Under the cold, dark water of the largest high-altitude lake in North America, the floor of Yellowstone is not flat. In the northern basin, sonar picks out a dome, a raised stretch of lake bed some 2,000 feet long, standing roughly 100 feet above the bottom around it, ringed with hot springs. It is not lava. There is no magma inside it. One interpretation is pressure from below, gas or hot fluid accumulating beneath a natural seal in the lake floor. What the dome means, and whether it matters for future hazard, remain open questions. And they are open in a landscape that has answered questions like this before, with some of the largest steam explosions in the geological record of the continent. 4 million people visit this park every year. Most of them stand within a mile of thermal ground that has, in the past, ruptured with little or no detectable warning. Almost none of them have ever heard the word for what it does. Yellowstone is famous for the wrong disaster.
Say the name and the mind goes straight to the supervolcano, the caldera the size of a state, the eruption that buries the Midwest in ash. The movie version where the whole continent ends in a single afternoon. That eruption is real geology, and it is also spectacularly unlikely in any human lifetime. The United States Geological Survey puts the odds in a given year in the neighborhood of 1 in 700,000. A rough estimate based on past intervals, not a prediction. The supervolcano is the threat everyone fears and almost no one will ever meet. Meanwhile, the thing that has actually hurt and killed people in this park, more than the bears, is hot water. And the geological record shows that the same hot water, at full scale, has torn open the ground here again and again on timescales measured in centuries and millennia, not in hundreds of thousands of years. The water is the part of the story the postcards never mention.
Iceland treats its steam fields as live hazards, and has for decades. Drill crews there have watched geothermal wells blow out and rain scalding mud and rock across a site. New Zealand learned the lesson with names attached. At Waimangu in 1917, a hydrothermal eruption tore through the valley and destroyed a tourist lodge beside the hot lakes, killing 2 people. On Whakaari, White Island, in December of 2019, a sudden steam-driven blast on an active vent killed 22 visitors who were standing exactly where the tours had taken them. Japan carries the heaviest version. In September of 2014, Mount Ontake produced a steam explosion with no fresh magma and little usable warning while hikers crowded the summit on a clear autumn Saturday, and 63 people died. The deadliest volcanic disaster in Japan's post-war history, from an eruption that ejected no lava at all. Same broad family of process, same shortage of warning.
Same lesson, learned separately on 4 different coasts. Yellowstone holds the largest known hydrothermal explosion crater documented on Earth, and it sits under a lake that 4 million people photograph every summer. For most of the 20th century, none of this was anybody's idea of a danger. The geysers were entertainment. Old Faithful was a clock you could set a schedule to. The hot springs were painted onto calendars and stitched onto souvenir patches. The steam explosions of the deep past were filed as Ice Age curiosities, events that belonged to a vanished world and had no bearing on the parking lots. The craters those explosions left behind were mapped, labeled, and then, in the way of comfortable places, quietly stopped being thought about. The ground had been showing what it can do, in the shape of holes big enough to swallow neighborhoods, the entire time. Nobody read them as a record of a live process. They were scenery.
So a handful of questions are worth setting down before going further. Why does the least famous part of Yellowstone's system, the water and the plumbing, not the magma, hold the hazard with the actual modern track record? Who decided that a crater more than a mile wide, blown open by steam in a single event, was a landform to name rather than a process to watch? Why do the busiest boardwalks on Earth run directly across live hydrothermal plumbing? And if the craters are mapped and the dome is measured, What exactly is a park of 4 million annual visitors standing on top of? By the end of this video, 3 things will be clear. It will be clear why survey teams who lowered instruments to the floor of Yellowstone Lake found a dome that no map had ever shown, and why its behavior is still being argued about. It will be clear why the largest hole steam is known to have blown open anywhere on this continent is not a canyon or a valley, but a bay you can paddle a canoe across.
And it will be clear what happened in July of 2024 when visitors with phones in their hands filmed one of these explosions arriving in front of them, and what it did to the boardwalk they had been standing on. Summer 2003. Norris Geyser Basin, the hottest, most restless thermal area in the park. Rangers walking familiar loops begin logging things that are not in any guidebook. New steam vents hissing in the pines, a stretch of trail hot enough to feel through boot soles. Springs that sat placid for years now churning near the boil. Ground temperatures in parts of the basin climb toward 200 degrees Fahrenheit, hot enough that trees begin to die standing, their roots slowly cooked in the soil. The park closes a section of the basin for the season. No eruption occurs, no magma moves. The plumbing beneath the surface has simply shifted, and the pressurized water and steam that circulate underground have found a new place to push. Eventually it settles, the trails reopen,
And the episode enters the record under the mild administrative label the scientists use for events like this: a thermal disturbance. A small, strange, easily forgotten reminder of how fast this ground can change its mind. That was the system twitching. To understand what it does when it fully lets go, you have to stand on the north shore of Yellowstone Lake, at the one place in the park where a hydrothermal explosion left a scar you can see from orbit. Mary Bay is a broad, curved inlet where visitors pull over to photograph the water. Almost no one who stops there knows they are standing on the rim of the largest hydrothermal explosion crater known anywhere on Earth. About 13,800 years ago, as the ice sheets were retreating and the first people were entering the continent, the ground beneath this spot detonated. Not erupted, detonated. Superheated water trapped beneath the lake floor flashed to steam, and the pressure blew open a hole 1.5 miles across, hurling rock and boiling mud outward in a violent pulse. The crater it left is the bay itself. The gentle curve of shoreline that families photograph on a summer evening is the wound. Walk the wave-cut cliffs between Storm Point and Mary Bay, and the sequence lies exposed in the dirt like a cross-section cut for a courtroom. At the bottom, the fine banded sediment of a quiet lake, laid down season on season. Above it, a layer of sand, which researchers read as the possible deposit of a wave thrown across the water by an earthquake. Above that, the breccia, angular rock, shattered and set in clay, the debris of the explosion itself. Stacked in order, bottom to top, calm, then a shock, then the sky coming down. What actually pulled the trigger is not firmly established. An earthquake, melting ice unloading the ground, a sudden drop in the level of the lake. And Mary Bay may not have been a single blast at all. The deposits allow for several explosions in close succession, a shoreline coming apart in installments. Mary Bay is not alone. The floor and margins of Yellowstone Lake are pocked with these craters: Elliott's Crater, Turbid Lake, Indian Pond. Each one the grave of a steam explosion, each one large enough to erase a town, and every one of them created without any eruption of magma whatsoever. Geologists have identified at least 25 craters in the park more than 100 meters across, and over the past 16,000 years, events at that size average out to roughly one every 700 years. An average is not a schedule, and it is not a countdown. It cannot be used to say whether the next large event is near or far. The true giants are rarer still. Every one of the largest craters formed thousands of years ago, most of them in the raw aftermath of the last glaciation. What the record says is narrower and harder to dismiss. This is not ancient, finished behavior. It is what this landscape does, at many sizes, and the smaller versions of it are still happening. The mechanism behind them is almost mundane in its ingredients, which is precisely what makes it worth understanding. Water seeps down into the hot rock above the Yellowstone magma system and is heated far past its ordinary boiling point, held liquid only by the crushing weight of the rock and water above it. Picture the pressure cooker on a stove. The water inside climbs well past 212 degrees without boiling, because the sealed lid keeps the pressure high. Then the lid comes off in a fraction of a second. Every degree of heat that water was storing above its normal boiling point is spent instantly turning it to steam, and steam wants more than 1,000 times the volume of the liquid it came from. A hydrothermal explosion is exactly that, a lid coming off.
Something drops the pressure on a pocket of superheated water. An earthquake cracks the seal, a landslide strips weight off the top, the lake level falls, or the plumbing simply reorganizes and opens a path. And the water that was holding its breath under all that rock exhales at once, upward, through everything above it. The trigger does not need to be dramatic. That is the uncomfortable center of it. Modest earthquakes, the kind Yellowstone produces by the thousand every year, can disturb shallow reservoirs. In 1989, a small explosion at Pork Chop Geyser in Norris Basin blew the feature apart in front of visitors, throwing rock fragments that landed more than 200 feet away. Nobody was hurt. Then, on the 23rd of July, 2024, at Biscuit Basin, a short drive up the road from Old Faithful, a pocket of the shallow plumbing beneath Black Diamond Pool let go in the middle of a summer morning. A dark column of boiling water, mud, and rock burst out of the ground beside a crowded boardwalk, shattered sections of the walkway, and sent visitors running through the falling debris. The footage is on their phones, an ordinary sightseeing stop becoming, in a single second, a live hydrothermal event. No one was seriously hurt. The park closed the basin, and geologists classified it as a small, localized explosion, a disturbance in the shallow plumbing with no change to the volcanic system beneath. Hold on to that word. The column that sent people sprinting down a boardwalk, that filled 100 phone screens and led the evening news, that was the small one. Most modern explosions in the park leave craters only a few meters across. Mary Bay is 1.5 miles. The distance between those two numbers is not a difference of degree a viewer can feel, it is a difference of category.
And the only honest way to hold both in one frame is this. July of 2024 is what this process looks like when someone happens to be standing there with a camera. The craters around the lake are what it left behind on the days nobody was. If the hidden hazards of this planet, the ones the textbooks and the tourist brochures leave out, are the kind of thing that pulls you in, subscribe to the channel and turn on notifications. There are more of these ahead, and every one of them is real. And now, back to the lake. The people who study this hazard for a living are not guessing. They lowered eyes to the bottom of the lake. Beginning in the late 1990s and running through the 2000s, teams from the United States Geological Survey and their university partners mapped the floor of Yellowstone Lake in detail no one had attempted. Sonar sweeps that rendered the lakebed as precisely as a topographic map of dry land. Robotic submersibles crawling the bottom. Instruments logging the temperature of vents no human eye had ever seen. Consider the conditions they were working over. Yellowstone Lake sits above 7,000 feet, and it is cold. Ice lingers on it into the start of summer, and a person who goes over the side is in serious trouble within minutes. Below the hull, the light gives out fast. The bottom is not a place divers go. What the instruments brought back from that darkness was not a dead basin. Hot water venting into freezing water. Sediment cooked and chemically altered by the fluids passing through it. Strange mineral spires standing on the lakebed like drowned chimneys. A floor already pocked with the sockets of old explosions. All of it invisible from a boat on a calm evening, under a surface that photographs like glass. And in the northern basin, south-southwest of Storm Point,
a feature that stopped the survey teams cold. A stretch of lake floor roughly 2,000 feet long, standing about 100 feet above the bottom around it, surrounded by hot springs, its sediments altered by the thermal water moving through them. Lisa Morgan, the USGS geologist who organized the lake surveys beginning in 1999, gave it an informal name that stuck: the Inflated Plain. Here is what can honestly be said about it. Seismic images of the sediment beneath the dome show tilted layers, a hint, and no more than a hint, that the ground there may have been pushed up from below. How much of that 100 feet is genuine inflation is unknown, and the researchers are explicit that it is likely a small fraction of the whole. The dome may be the surface expression of gas or hydrothermal fluid gathering beneath a natural seal, a lid with pressure under it. Its origin and its behavior are still being studied. In recent years, research teams have wired the lake floor itself with instruments to listen to it. When word of a bulge at the bottom of Yellowstone Lake first reached the press, the USGS was blunt in the other direction. No evidence of immediate danger, no sign of runaway growth. Both of those things are true at once. No indication it is about to fail, and no ability, yet, to say what it will do on a timescale that matters to anyone alive. And that is the honest source of the unease. The unsettling part is not the dome itself. It is the company it keeps. The same lake floor holds the craters of enormous hydrothermal explosions that already happened, and the same ingredients that produced them, heat, water, pressure, and a seal, are still present, still interacting, right now, in the dark. Nobody can tell you whether the next large hydrothermal explosion in Yellowstone, if one comes, will break from the lake floor or from a basin on land, in this generation or in some other century. The geology does not offer a date. What it offers, written in the deposits of the explosions that already happened, is a description of the event. So consider the event, the way scientists reconstruct it from the rock, played forward from the instant a seal fails. The failure begins underground, in a reservoir of water that has sat superheated and sealed for years or decades, and it moves at the speed of physics. Pressure on the reservoir drops, an earthquake, a shift in the plumbing, a slope letting go. In the first fraction of a second, the top layer of trapped water flashes to steam and expands upward with explosive violence. That expansion tears open the rock above it, which drops the pressure on the water beneath, which flashes in turn. A chain reaction unzipping down through the superheated column even as it blasts upward through the ground. At the surface, the ground does not rumble and then break. It opens. A column of steam, mud, boiling water, and rock erupts upward and outward, and the material rains down across everything within reach. Blocks thrown by the large explosions in the geological record have been found miles from their craters. The water arrives above boiling, and the violent phase, the part that kills, is over in minutes, sometimes in less than one. Now place the hazard where the people are. The most crowded ground in Yellowstone is not the lakeshore. It is the upper geyser basin, the boardwalks around Old Faithful, the visitor center, the historic lodge, the parking for thousands of cars, gathered on top of one of the densest concentrations of hydrothermal features on the planet.
Every geyser and spring on those boardwalks is fed by the same kind of superheated, pressurized plumbing that has produced explosions elsewhere in the park. And the 2024 Biscuit Basin blast went off a few minutes' drive from these walkways. USGS scientists describe hydrothermal explosions as among the Yellowstone geologic hazards most likely to directly affect people, for a simple reason. They occur in thermal areas, and thermal areas are exactly where the visitors go. Scale matters less than proximity. Even a small, localized explosion, a Biscuit Basin, not a Mary Bay, can wreck infrastructure and endanger anyone standing near it, because the boardwalks exist precisely to bring people close. None of this makes Yellowstone unsafe to visit. It means the famous danger and the documented one are not the same thing, and only one of them has gone off in front of camera phones. The gap here is not a story of negligence. It is a story of a hazard that hides behind a more famous one.
The science has done its work. The Yellowstone Volcano Observatory watches the whole system around the clock. Seismometers, GPS stations, satellite radar, stream gauges, temperature sensors. And the monitoring is good enough to watch the entire caldera rise and fall over the years, a slow breathing measured in fractions of an inch. The asymmetry comes down to size, depth, and speed. Magma is enormous, it sits deep, and it cannot move without shouldering a mountain of rock out of the way, which is why it announces itself for weeks, swarms of earthquakes, ground that swells, gas that changes its chemistry. A pocket of hydrothermal water is none of those things. It can be shallow, it can be small. It already sits at the temperature where water and steam trade places, and it can be tipped across that line by a pressure change slight enough to disappear into the ordinary background noise of a park that produces between 1 and 3,000 earthquakes a year. Small trigger.
Small signal. The record shows these events often arrive without clear precursors, leaving little or no actionable warning, and once the seal goes, the event is measured in seconds. Since 2024, researchers have been adding instruments in the thermal basins, listening for whatever a system might say before it fails, work that is ongoing, and candid about not yet knowing whether a reliable signal exists at all. Park managers do the things that can be done. They watch the instruments, close ground that starts behaving strangely, as they did at Norris in 2003 and at Biscuit Basin in 2024, and keep visitors on boardwalks, which removes most of the thermal risk a person can actually control. What remains is the residue no instrument has solved, an event that can begin faster than any alert can travel, in a landscape built to gather crowds. The instruments watch the magma closely. The water keeps its own counsel. And the system is demonstrably alive. In September of 2018, year spring, a quiet pool on Geyser Hill that had barely erupted in decades suddenly blasted out a column of hot water, and with it, generations of debris. Coins, cans, a warning sign, a pacifier dated to the mid-20th century. The sediment of 80 years of tourism returned to sender in a single afternoon. A year later, park scientists announced something stranger. A brand new thermal area, discovered in satellite and aerial imagery, that had quietly cooked itself into existence in the backcountry near Tern Lake over roughly 20 years. Trees killed, ground warmed, an entire new patch of live hydrothermal terrain assembled without a single visitor noticing. That is what a thermal disturbance in the scientists' reports actually describes. The ground rearranging the pathways of its superheated water, sometimes cooking a trail, sometimes killing a stand of pines, and across the long span of the post-glacial record, sometimes blowing open a crater you can see from orbit. The craters around Yellowstone Lake are the entries this system has written so far. Whether the list is finished is a question the science cannot close. And that open question, not any countdown, is the honest shape of this hazard. A strange humility waits in this landscape for anyone who understands what they are looking at. The gentle curve of Mary Bay is a crater. The placid round pond by the road is a crater. The flat basin where the boardwalks run sits above water so hot that at depth, only pressure keeps it liquid. We cross it in sandals and photograph the geysers and call it a park. Because in a single afternoon, in a single summer, in a single human lifetime, it holds. Usually. The word usually is doing an enormous amount of work in that sentence. Across thousands of years, this ground has kept its lid on for long stretches. And then, on occasions the record preserves in stone, taken it off with little warning anyone could have read. The scenery is the archive of every time it did. The craters are the only witnesses that were present. They cannot say when or where or at what size the next explosion might come. No one can, and any voice claiming otherwise is selling something. Wood keeps time in rings, and mud keeps time in layers. But a hole in the earth 1.5 miles wide keeps only one fact, and it keeps it perfectly. The water under this ground did this once, at this scale, in a single violent stretch of minutes. And heat, water, and pressure are still down there, still interacting, still sealed. The bay does not argue, it does not predict. It curves along the shoreline in the evening light, a mile and a half of quiet water sitting in the socket of an old explosion, waiting for anyone to stop and understand what made it. If the deep, indifferent memory of the planet, the catastrophes it has already survived, and the hazards it still carries, is the kind of thing you want more of, subscribe and turn on notifications so the next episode finds its way to you. There are more landscapes hiding this kind of record, and more of them are worth listening to.
Somewhere beneath the boardwalks, and somewhere under the cold water of the northern basin, superheated water sits sealed beneath the weight of rock. The same broad ingredients of heat, water, pressure, and sealed pathways that have produced explosions elsewhere in Yellowstone. Mary Bay, Turbid Lake, Indian Pond, the craters with names and the ones without. Scientists consider future hydrothermal explosions possible. No one can predict when, where, or how large the next one might be, whether it would break beneath an empty stretch of lake or near a summer crowd, whether it comes in this century or far beyond it, whether it wrecks a boardwalk or makes a bay. Worth carrying out of this. Not one of the large hydrothermal explosions of the last 16,000 years was followed by an eruption of magma. The water does not wake the volcano. The water is its own story, smaller than the one that sells the movie posters, and the only one of the two with a modern track record.
The survey puts it in language that refuses both panic and comfort. Events on this scale are rare on a human timescale, and the potential for another is not insignificant. Both halves are true. Most people who walk these boardwalks are only ever told the first. The danger is not that catastrophe is imminent. The danger is quieter and stranger than that. The hazard is real, it is sudden, it is active on human timescales. And almost no one who walks this ground has ever heard its name. The famous monster of Yellowstone sleeps on a clock of hundreds of thousands of years. The water above it keeps a different kind of record, written in craters, and it does not share the dates. The floor of Yellowstone holds the record of every explosion so far. Read it honestly, and the lake stops looking like scenery. It starts looking like a ledger, patient, accurate, and open to a page that no one on Earth can fill in.